Hi, everyone. My name is Ruoxi, and I'm a postdoc in Materials Project Group. And today I'll be introducing you the code called Pymatgen. And first of all, let's make sure we are in the right place to open this notebook. So let's go back to the files. If you're in CodeCalc, click on Files. And I'm already in this folder called Workshop Lesson. If not, if you are in the home directory, for example, this place, you can go to the folder called Workshop. And within Lessons, you can find the intro, Pymatgen here, and click on it. Right now, I have created an empty notebook and the actual lesson, which is Pymatgen Foundations. In there, it has all the command lines or the codes that are already written. But today I'll be using this empty notebook to type along. You can follow me. So to do that, you can create a new Jupyter notebook by clicking this button, New, here. And you can change the name of the Jupyter notebook, and in there, you click the button Jupyter notebook. And now you're in a brand new notebook where you can type along with me, which I recommend you doing. So I'll close this notebook for now, and I'll be using this empty notebook that I already created with some structure here. So let's get started. So you have already heard the nice introduction Materials Project website from Cody. And Pymatgen is the actual code that powers all of that scientific analysis behind all the information you see on Materials Project. It includes many robust and efficient libraries for the handling of the crystallographic structures and molecules, in addition to various mathematical and scientific tools for handling and generation of materials data. And since it has so many libraries, today I'll be only covering the most basic modules within Pymatgen, that is structure and molecule. So if you attended yesterday's primer, you would know how to install Pymatgen. It's very easy. You can use pip or conda. But for the purpose of this workshop, Pymatgen is already installed, so I won't repeat how to do that. So let's verify first if we have Pymatgen installed. We can do that by simply enter import pymatgen.core and press Shift Enter or this button Run here. And Pymatgen is already imported through this. And we want to check what specific version of Pymatgen is installed on this Jupyter notebook environment. We can do print bracket pymatgen.core __ version and _ and Shift Enter. You see that it's the newest version of Pymatgen installed in this environment. And let's check out where Pymatgen is installed on our computer. We can do print bracket pymatgen.core _ file and _ and it tells you where this library is installed in your computer. We can also check out which version of Python we are using by doing import sys and print sys.version. And it's the Python 3.9.0 that we're using. These are important information for example, debugging if you run into any problems with Pymatgen, and these are the places we're going to look for. Okay, so we verified that we have all the necessary package installed. We'll start the actual lesson. So today I'll be covering structure and molecules. These are the most fundamentals of Pymatgen, which are used to handle crystal structures or molecule structures. The main difference is that the structure supports full periodicity required to describe crystallographic structures, while molecules doesn't. Creating a structure is very easy. You can do that in one line, even for very complicated crystallography structure. However, we'll start by introducing the somewhat simpler module called Molecule Object, and then use the understanding of molecule to introduce structure later. So we'll start by creating a molecule. First, let's import the object. So import pymatgen.core.structure. Oh, sorry, I should do from Pymatgen core.structure because we already imported Pymatgen.core. So from this place, we import molecule and press Shift Enter, it'll run and it's imported. So let's type molecule and see what happens. Molecule. So in the Jupyter notebook, you can show the help of a particular object by clicking, by pressing Shift and Tab. And pressing Shift and Tab, and you see below this line, there is the documentation for this Python object, which includes the necessary arguments. If you scroll down, you can see the documentation of what this object does. And the necessary argument, in this case, the mandatory arguments are species and coordinates. And it tells you what form of the data you need to input. And also it includes the keyword arguments, which are charge, spin, validate proximity, site properties. These are optional, which comes with a default value, and you won't worry about them too much, but the mandatory ones are the species and the coordinates. Okay, let's close this window and press Shift Enter, and it shows the object of molecule. And now we can start create a molecule. Let's start from a simple one, a carbon monoxide. So here we define a C_monox using the molecule object. So capital M molecule bracket. As you remember, the first positional argument is the list of elements. So we are entering a list, Python list. So carbon and oxygen. And the second positional argument is the list of coordinates, which is a two-dimensional array. So here I'm entering the Python list. Remember, there's two lists here as they correspond to the Cartesian coordinates of the corresponding element. So for carbon, it's 0, 0, and 0. And for oxygen, another list, 0, 0, 1.2, and print C_monox. Okay, it shows the full formula, the reduced formula of this C_monox object, and it contains no charge, no spin, and two sites which correspond to the ones that we just entered. So for carbon, it's the 0, 0, 0 site, and for oxygen, this site. And now let's try using a keyword variable to change the default value. For example, the charge here. How do I do that? We can try construct a OH minus anion. So OH_minus equals to invoking molecule here, molecule, bracket, entering the list of element, O and H. The list of Cartesian coordinate, so 0, 0, 0. I need to enter 2 lists here. Okay, and for oxygen, for hydrogen, sorry, 0, 0, and 1.0. And now we specify the charge. So by simply doing charge equals -1 and parent COH minus. And now we have the formula of this OH anion with a charge of -1 that we just specified, and still this default spin value and 2 sides. Alternatively, we can also create molecule objects from a file. Let's say we have an XYZ file called water.xyz, which is already provided in our workshop in this folder. We can import that file using a method called from file like this. So we define an object called water equals molecule from underscore file. And the input is the file name, which is in the form of a string. Remember the quote here. So water.xyz. And let's print water. Okay, so it takes in the XYZ file in the folder and convert it into this Python object, which is H2O with 0 charge and no spin. And it contains 3 sides, which is the oxygen and 2 hydrogen. And in this folder, I have already provided you some other files for different molecules. You can try it yourself. You can enter more cells, by the way, by pressing this button plus here, and you can enter as many as you want, where you can specify the molecule that you want to try out in our folders. And I'll give you a couple of minutes to try that. And I will be introducing you the properties of this object momentarily. Okay, so now we have played with how to import a molecule from the file. Next, I'll be introducing sites, element, and species in a molecule. So a molecule object has many attributes or properties. We can check them out using, for example, print here. So print bracket. We just constructed the C monox, so C underscore monox dot. Now we want to know what the Cartesian coordinate is for this molecule. So we type cart underscore coords, and it prints out the list of the Cartesian coordinates of the site that this molecule contains. So essentially, a molecule object is a list of the site of the element. There are also properties that are computed on the fly, such as the center of mass. So let's print C underscore monox bar center of mass. And you see that the center of mass is in between the carbon and the oxygen atoms. And this property is computed while we enter this command here. And what if I want to change the property of a molecule after I created it? Is there a simple way to do that? So for example, I want to change the charge of this carbon monoxide molecule. I can do that by typing C underscore monox dot using the method called set underscore charge and spin. And in the bracket, I input the charge I want to use, which is 1. And let's print C underscore monox and press Shift Enter to run the cell. Now you see that in addition to the carbon monoxide we just created, there's a 1 positive charge in there. So we added this property after we created this molecule. So since a molecule is essentially a list of site objects, we can access these sites like we would in a Python list. So for example, let's check out how many sites are in this carbon monoxide object. We do that by doing len and C underscore monox. So this tells us how long the list is. So in this case, 2, because we have 2 species in this molecule object. And what if we want to access the first site? We can do that by doing print, let's see, C underscore monox 0, which is the first site in this list. Okay, we see that it's 0, 0, 0 carbon. And just like that, I can exchange the position of the sites by specify the site. So now the first site is a carbon. I want to change it to the oxygen. How do I do that? I can do this. So C underscore monox 0 now equals to oxygen, and C monox 1 equals to carbon, and print this molecule. And comparing to the one that's just printed earlier, you see that oxygen and carbon has exchanged the site. So a site object also contains some properties. So let me add more cells to this notebook here. Okay, so let's define a site called site 0 equals to C monox 0. And what properties does it have? Let's check out. So site 0, for example, cohorts. It's an array of the Cartesian coordinate of the first site in this molecule. And it also has site 0 species. And it says its element oxygen, because we switched the position of the site early on. So in general, a site can hold either an element or a species or a composition, and we can look at each of them in turn. So to do that, we need to import these modules. So from pymatgen.core.composition, we import element with capital E and composition with capital C. And from pymatgen.core.peri periodic table, import species. Add more cells here. And let's define a carbon element. So carbon equals, invoking the module element here. And the input is the string of the element you want to use. So C in this case. Sorry, I typed 2, 0 here. Okay, and this element carbon has properties such as atomic mass, average ionic radius, and more. So let's check out the average underscore ionic radius, and it's 0.3. So then I'll be using the module species to construct a species that has more information than just an element. So for example, I want to do a oxygen ion. So O underscore ion. And using species with capital S, the input takes in the string of the element, so oxygen, and we can specify the oxidation state in the module species. So oxidation state equals to -2, and print O underscore ion. We see that it's O2 minus. And we can access the property of this ion by typing O ion dot oxy state, and tells you that it's -2. Adding more cells to this section. And it also has the atomic mass. So O ion dot atomic underscore mass. It's 15.9994. And okay, for convenience, we can also use a string to construct a species, which will be interpreted as elements with an oxidation state. We can do that very easily by using the method called fromString. So here I'm using species from underscore string. And in this method, you just simply provide the string that contains the element oxygen and the oxidation state, in this case 2-. You just write them together. And here we have a species O2-, just like we did in this method. And finally, a composition is an object that can hold certain amounts of different elements or species. This is very useful in a disordered structure, but would rarely be used in a molecule. For example, a site that holds 50% gold and 50% copper would be set as follows. Let's define a composition called comp equals to, using the Python object called composition. The input file takes in a dictionary. So in this case, gold in the form of a string, and it has 0.5 gold. Oops, sorry. Copper also 0.5. And let's check out the formula of this composition and the chemical system. So print string formula, comma. Now we access the property of this composition we just created. So comp dot alphabetical underscore formula and print the chemical system, which is the comp property chemical underscore system. And it prints out the formula which we just created, which is copper 0.5, gold 0.5, and copper 0.5, and has a chemical system of gold and copper. So for the exercise, we want to construct a hydrogen cyanide where we create this linear molecule where each bond distance is the sum of the two atomic radii. And I can show you how we do that. So first we need to know the atomic radius of these species. And we need to do H ray. So define the radii of hydrogen atom equals to, we want to use the element hydrogen here. So how do we do that? We use the object element and input file, input argument H, and has the property of a atomic underscore radius. And similarly, we do that for the carbon atom. So carb rate equals to element carbon atomic radius, and nitrogen rate equals to element N and atomic radius. Okay, now we define these variables. We can construct the bond length or bond distance between the pairs of species. So we do that by, say, Hc bond dist equals to, using the variable we just defined, H radius plus the carbon radius. And how about the Cn bond distance? So Cn bond dist equals to C rate plus nitrogen radius. Okay, now we have the bond distance. We want to put the species at specific positions in this molecule. As I already showed you, we can do that by specifying the position. So H plus equals to 0, the original point. And the carbon position would be the hydrogen position plus the bond distance between them. So Hc bond dist, and the nitrogen position will be the carbon position plus the Cn bond distance. These are simple because this is a linear molecule, so it's very easy. You can just do it this way. But for non-linear molecules, it can be trickier. Now with all this information, we can construct the HCN molecule now. So define HCN equals molecule. Input the list of elements, H, C, N, and the list of the coordinates. So first one corresponding to hydrogen that we just defined. So H position and 0, 0. Because it's a linear molecule, we already specified the latter two coordinates to be 0, but only changing the X value. And the second one is carbon plus and 0, 0. And last one, nitrogen, so plus 0, 0. And print this molecule, HCN. Here we go. We see that this linear molecule is constructed using the atomic radius and the position of these atoms. And hopefully you get an idea of how to use this molecule object to construct a molecule, and you can play with it for a little bit. And for the next section, I'll be introducing you the module called Structure and Lattice to create crystal structure with periodicity. I'll give you 2 minutes to play with this method a little bit, and I'll resume very soon. Okay, hopefully you have some time to explore what the molecule object can do. And in this section, I'll be introducing you the module called Structure, which is very similar to creating a molecule, except that now we have to specify a lattice. So let's do that by import this module first from Pymatgen.core. We import lattice and structure. Since structure is the object for a crystallographic structure, it contains the information of the lattice. A lattice object can be created in one of the several ways, such as by inputting a 3x3 matrix element, describing the individual lattice vectors. For example, a cubic lattice of a length 5 angstrom would be, here we define my lattice equals to using the object lattice with capital L. And what input it takes in. So you can check that by pressing Shift and Tab. And it shows you the argument, which is a matrix that looks like this. So we know what types of argument it goes in. Let's specify this cubic lattice. So 5, 0, 0. And the second line is 0, 5, 0. And the third line is 0, 0, 5. Okay, and let's print my lattice. Press Shift Enter to run. Okay, and you see that it's a 2-dimensional array with a 5, 5, 5 ABC vector for our lattice, and it's a cubic. Equivalently, we can also create it from the lattice parameters. In this case, I define another object called myLattice_2. And this time I'm using this method called lattice from parameters. And it takes in the value of the ABC vectors, 5, 5, 5, and the angles of alpha, beta, gamma. So 90, 90, and 90. Let me add more empty cells here. And what does it look like? Print my lattice 2. Okay, it's exactly the same as the one we just specified earlier. And we can use another method called cubic, which is a method that specifies a cubic lattice. Let me show you how to do that. Lattice, sorry, my_lattice 3. I define a new object using lattice. Now this time I simply using the method called cubic and provide the lattice parameter, which is 5. And we have the myLattice 3. Okay. And to see if they are equal to each other, we can use this statement, myLattice equals to, using 2 equal here, myLattice 2 equals to myLattice 3 to see if it's true. And it indeed is true. So these 3 are equivalent ways to construct a cubic lattice. Okay, now we have the object of a lattice. We can start create a simple crystal structure. Let's start with the most simple body-centered cubic iron. How do we do that? We start by defining an object called BCCFE equals to structure. So I'm using the object structure with a capital S here. First, we need to specify the lattice. We can check out the argument first. So in this case, the argument, the positional ones are lattice, species, and coordinates. These 3 are the mandatory argument with a few optional argument as well. As you can see, it's very similar to molecule as well. So now we know what arguments goes in this object. It's putting the lattice first. So we use the simple method called lattice.cubic, and it has a 2.8 lattice parameter. And the second argument is the list of element, in this case, Fe and Fe. And the third one is the coordinate, 0, 0, 0, and 0, 0.5, 0, 0.5, and 0, 0.5. It's important to note that in this case, when we use structure, the coordinate become a fractional coordinate instead of the Cartesian coordinate that we use in molecule. And let's print this BCCFE. Okay, so it prints out the full formula and the reduced formula of this object we just created. There's a 2.8 lattice parameter, which is cubic, as you can see here, and it contains two sites on the high symmetry point, like we specified at these two sites. So creating this structure was very similar to creating a molecule in that we provided a list of the elements and the list of positions. The key differences between structure and molecule is that we have to include the lattice object when creating this structure, since we have a lattice for the crystal. And we define, the second difference is we define the position of our sites in fractional coordinates with respect to the lattice instead of the Cartesian coordinates. So there's another way to create an equivalent structure using Cartesian coordinates too. I can show you how. Adding more cells here. So let's define BCCFE from underscore cart equals to structure. And similarly, lattice dot cubic, sorry, 2.8, and list of element Fe, and list of the Cartesian coordinate we want to use. So 0, 0, 0, and 1.4, 1.4, and 1.4. But we need to tell this object that we are using Cartesian coordinate. We do that by specifying this argument called coords underscore r underscore Cartesian equals to true. And now the structure class will recognize these list of coordinates to be Cartesian. And let's print BCCFE from cart. And as you can see, these two are exactly the same because molecule translates the Cartesian coordinate to be a fractional one. So they are still residing on the same position as the one we specified earlier. Let's check out if they're equal to each other. BCCFE equals to BCCFE from cart. And they are exactly the same. So as in a molecule, we can also access properties of the structure, such as its volume. BCCFE dot volume is 21.9. And we can also create structures from a space group that we specify. So in this case, I'm skipping these two empty cells using the structure below. So again, we define BCCFE equals to structure. But this time I'm using the method called from underscore space group. And I'm inputting the name of the space group for this body-centered iron, which is IM-3M. It should be bar 3, but for the simplicity of this string, we use -3. And the second argument is the lattice. So similarly, lattice dot cubic 2.8 and list of element, in this case, iron. And note that now that this time we're using the method called from space group, it automatically fills in the high symmetry position for the atoms. So now we only need to specify one element, which is iron, which should still be in the form of a list. It's important to note the bracket, square bracket here. And the position of iron, which is 0, 0, and 0. And let's print that. Okay, so you note that although we only specified one element, iron, and one position, because we provided also the space group, structure can put an additional atom at the high symmetry point as well, and it's equal to the one we just created. And let's try out, construct a 2-atom unit cell. So let's try doing a sodium chloride. So NaCl equals to structure from space group. And in this case, the space group is a face-centered cubic. So Fm minus 3m, and the lattice cubic with the parameter, lattice parameter 5.692, and the list of elements or species, in this case Na plus. Note that I'm adding the oxidation state into the species too. And chlorine minus. And the coordinate 0, 0, 0, and 0.5, 0.5, 0.5. And print NaCl. And look what we have. It has a reduced formula of NaCl, but the full formula is 4 sodium and 4 chlorine. The lattice is cubic with the same lattice parameters and 90-degree angle. But because we specified these, this face-centered cubic space group, it automatically fills in the high symmetry positions for the other ions as well in this unit cell. So let's check out the space group of this structure we just created. We can do that by access the get space group info. I'm adding the bracket meaning in the end because it's a method. It tells you that it's a FM 3 bar n space group with a number of 225. So yeah, we now have the space group info using this simple method. All right, so now we are well prepared in the art of creating a singular structure, but sometimes we don't just want one unit cell, we want a supercell. Pymatgen can provide a very simple interface to create a superstructure. And let's start with the simplest structure that we can imagine, which is polonium, a simple cubic metal. Let's define the unit cell first. So polonium equals to structure, and providing the lattice dot cubic 3.4 lattice parameter, the element PL, and the coordinate 0, 0, 0, and print polonium You see we have a simple unit cell now. To make a supercell of this structure, we can just multiply the structure by a tuple. It's very simple. So we define a supercell equals to, using the unit cell we just created called polonium, and times a tuple is a bracket. So now I want a 2 by 2 supercell. I just do 2, 2, 2 tuple and a print supercell. Okay, so you can see that now the unit cell is transformed into a 2 by 2 supercell because you see that there's 8 atoms now in this supercell, and the A, B, C lattice parameters are all doubled and maintaining the 90-degree angle for the alpha, beta, gamma. And there are 8 sides in this supercells as well. It's very simple. Okay, the last bit is an exercise where we create a barium titanate supercell from the CIF file that we already provided in the folder. Let's try replace the barium with a new element with the atomic number equal to the day of the month you were born. And then you make a supercell of n unit cells in one Cartesian direction of your choice, where n is the integer of your birth month. For example, January would be 1. Let me show you how to do that. So first we define a BATI03 equals to structure from file using the same method as we introduced in the molecule object. So structure has the same method called from file, and providing the file name in the form of a string. So BATI03.CIF and print BA. Let's check out what the space group it is. TI03.get space group info. Remember to put another bracket after this method. It's a R3M with the space group number 160. And let's see what it looks like. So print BATI03. Okay, it tells you the position of the sites with barium, titanium, oxygen in there. And now I want to replace barium with magnesium, for example. How do I do that? There's a simple method called replace. Let's try it. So BATI03.replace. Inside, I'm specifying the site that I want to replace, in this case, barium, so 0. And the element that I want to replace with, in this case, magnesium. And now we have a magnesium atom sitting at the original position of the barium, as you can see. And now I want to create a supercell of this barium titanate. How do I do that? Just like I showed you earlier. So BATI03 equals itself, BATI03 times. So in this case, I want to do a 1 by 1 by 4 supercell. So 1, 1, 4 tuple. Let me add more cells here for you to see. And print BATI03. Okay, now we have a supercell of this unit cell that we created earlier. So it has 4 magnesium now and 4 titanium, 12 oxygen. And the ABC. So AB is the same, but for the C direction, it has 4 times the original value. And okay, we also have these 4 sides for each element as well. And to see if it still has the same space group info, we do print PATIO3 dot get space group info with a bracket and shift enter. Still, it's the 160 space group number. Okay, so this is all to the introduction of Pymatgen lesson. I hope I have conveyed to all of you that how to use the basic module called Molecule and Structure and Lattice. And hopefully you will have a better idea of what Pymatgen can do in terms of structure. And that is all to our lesson. And you have some more time to play with this method on yourself. And thanks for your attention.